Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome to the deep dive. Today, we're going to be taking a close look at the world of quantum computing, specifically focusing on Google's new Willow chip.
Right.
You've given us a document titled Willow, a quantum leap in computing, and we're going to break down what makes this technology so potentially revolutionary.
The best way to understand Willow and its implications is to first grasp how quantum computing differs from the classical computing that powers our everyday devices.
That's a great point. Classical computers, whether it's your phone or a powerful supercomputer, rely on bits for information processing. Each bit can be either a 0 or a 1.
Right.
All the complex computations we perform boil down to manipulating these bits.
Quantum computers, on the other hand, use qubits, which are governed by the principles of quantum mechanics.
Okay.
A key difference is that a qubit can be 0, 1, or both simultaneously, a state called superposition.
Superposition is indeed a key concept. Imagine a coin spinning in the air before it lands. Until you stop it and observe it, it's in a state of being both heads and tails. That's similar to what's happening with a qubit in superposition.
And there's another important principle, entanglement. When two qubits are entangled, they are linked, regardless of the distance between them. Measuring the state of one instantly tells you the state of the other.
This interconnectedness is crucial because it allows quantum computers to explore many possibilities simultaneously.
Yes.
In contrast, a classical computer would have to examine each possibility one by one.
The document offers a helpful analogy to illustrate this. Imagine you're trying to solve a maze. A classical computer would need to try each path sequentially until it found the exit. A quantum computer, leveraging superposition and entanglement, could explore all paths concurrently, significantly accelerating the process.
This inherent parallelism has profound implications, particularly when considering tasks like factoring large numbers, a process crucial for cryptography, which secures our online communications.
Classical computers struggle to factor large numbers efficiently. That difficulty is actually a cornerstone of modern encryption.
However, a quantum computer running Shor's algorithm could factor those numbers exponentially faster, posing a potential threat to current cryptographic systems. This is why researchers are also exploring quantum-resistant cryptography as a solution.
Now let's shift our focus to Willow and its specific advancements.
Okay.
Willow tackles a major challenge in quantum computing, scaling.
Right.
This involves increasing the number of qubits while maintaining their stability and coherence.
The document highlights Willow's achievements in this regard, particularly its ability to handle a significantly higher qubit count than its predecessors. This allows it to perform more complex computations, pushing the boundaries of what's possible with quantum computing.
Willow's success in scaling is largely attributed to its innovative architecture. It utilizes a novel topology that ensures each qubit can directly interact with multiple neighboring qubits, resulting in faster and more efficient computations.
This enhanced connectivity contrasts with earlier systems that relied on limited interconnections, which hampered their speed and efficiency.
The document also emphasizes the advanced materials integrated into Willow's design. These materials help reduce interference and maintain coherence for longer periods, addressing the inherent fragility of quantum states.
Earlier quantum computing systems relied on superconducting materials that were more susceptible to noise and environmental factors, limiting their potential for complex computations. Willow's advanced materials represent a significant step towards mitigating these limitations.
While these advancements are remarkable, it's important to remember that quantum computers are inherently prone to errors due to decoherence and noise. These errors can disrupt the delicate quantum states and introduce inaccuracies into the computations.
The document mentions that Willow integrates advanced error correction protocols to address this challenge, specifically highlighting surface code error correction. Can you elaborate on how that works?
Surface code error correction involves arranging qubits in a lattice-like structure. This structure helps detect and correct errors without disrupting the ongoing quantum computation.
It's almost like having a built-in safety net that constantly monitors and corrects errors, ensuring that the computation stays on track.
That's a good analogy. This approach is a significant advancement over previous error correction methods that were less efficient and often disrupted the quantum state. Willow's error correction protocols contribute significantly to the reliability of its computations.
The document also mentions enhanced algorithms that play a role in minimizing errors.
That's correct. Willow incorporates algorithms specifically designed to reduce the overhead associated with error correction.
Okay.
This means that more qubits can be dedicated to the actual computation rather than being tied up in error management, increasing the system's overall efficiency.
The document further highlights dynamic feedback systems as a key feature of Willow's design. Can you explain how these systems contribute to the stability of the computations?
Dynamic feedback systems are designed to constantly adjust the operational parameters of a quantum computer in response to environmental noise. This real-time adaptation helps to counteract the destabilizing effects of noise, ensuring a more stable platform for complex computations.
So they're constantly monitoring and fine-tuning the system to maintain the coherence of the qubits, much like an engineer adjusting settings to optimize performance.
Precisely. These dynamic feedback systems play a crucial role in ensuring the accuracy and reliability of Willow's computations by counteracting the inherent fragility of quantum systems. All of this points to a system that's more stable, efficient, and ultimately more practical for real-world applications. But the practical aspects of operating a quantum computer are also important.
That's right. We know that quantum computers require extremely low temperatures to function, often cooler than outer space.
Right.
Does Willow address the energy demands associated with this extreme cooling?
It does. Willow incorporates innovations in cooling and energy management, a significant step towards practicality. Its design aims to minimize the energy consumption required for maintaining these ultra-low temperatures, making it a more viable solution for wider use.
That's an important consideration, especially as we look towards a future where quantum computers might be more commonplace. But what about the programming aspect? How accessible is Willow to scientists and researchers who want to harness its power?
Willow is designed to work seamlessly with quantum programming languages like Cirq, which are already being used by researchers in the field.
So while quantum programming remains a specialized field, the tools are there for scientists and researchers to start developing and testing applications for Willow. Are there any examples of successful applications already being explored?
Yes, there are. Researchers have successfully used Willow to simulate molecular interactions in complex chemical reactions, a task that is computationally very challenging for classical computers. This has significant implications for drug discovery, potentially revolutionizing how we design and test new therapies.
It's fascinating to think that we could potentially design and test drugs entirely in a virtual environment, using quantum simulation, accelerating the process, and potentially leading to breakthroughs in treating various diseases.
Absolutely. Another promising application is in optimization problems. The document highlights Willow's success in optimizing logistical problems, such as finding the most efficient routes for supply chains.
This demonstrates the versatility of Willow and its potential to address a wide range of computational challenges across diverse fields. So we've covered the fundamental differences between quantum and classical computing, explored Willow's key advancements in scaling, error correction, and efficiency, and even touched upon some early successes.
Indeed. Now, the key question is, what does all of this mean for the future? What real-world impact can we expect from quantum computing, and what's the realistic timeline for these advancements?
That's what we'll delve into next, exploring the potential applications of quantum computing and their estimated timelines for practical implementation.
The document provides a realistic timeline for when we can expect quantum computing to have a significant impact across various fields. One area ripe for disruption is optimization problems. We're talking about optimizing supply chains, transportation routes, financial portfolios, even the design of complex systems.
The document suggests we could see practical applications in these areas within the next 5 to 10 years. Why is that time frame realistic?
Quantum computers excel at solving optimization problems that would take classical computers an impractical amount of time due to their ability to explore multiple possibilities concurrently.
So businesses could leverage this to make significant cost savings and efficiency improvements.
Absolutely. Imagine a world where goods are delivered faster and more cheaply, traffic flows more smoothly even during rush hour, and companies can make better decisions based on real-time data analysis. These are the kinds of improvements quantum computing could bring to optimization challenges.
Another area where quantum computing could have a profound impact is cryptography and security. Earlier, we discussed the threat quantum computers pose to current encryption methods like RSA.
That's right. What takes a classical computer years to crack, a quantum computer running Shor's algorithm could potentially do in a fraction of the time. This vulnerability applies to much of our sensitive data, from financial transactions to national secrets.
But the document also highlights the potential for quantum computers to create new, unbreakable forms of encryption known as quantum cryptography.
Indeed. It's an exciting area of research. One promising approach is quantum key distribution. It uses the principles of quantum mechanics to ensure that any attempt to intercept a message would be immediately detectable.
So unlike current encryption methods that could be vulnerable to undetected breaches, quantum key distribution offers a way to detect any eavesdropping attempts.
Precisely. The document suggests that we could see practical applications of quantum cryptography, like quantum key distribution, within the next 5 to 15 years.
Moving on to a different field, the document discusses the potential of quantum computing in drug discovery and materials science. It highlights the long-term potential in these areas, but suggests a longer timeline for practical applications.
One of the biggest challenges in drug discovery is simulating the complex interactions between molecules. This is a computationally demanding task that classical computers struggle with, limiting our ability to design and test new drugs efficiently.
The document suggests that quantum computers, with their ability to directly model quantum systems, could revolutionize this process.
Exactly. They could allow scientists to accurately simulate how drugs interact with the human body at the molecular level, leading to the development of more effective and targeted therapies.
And these advancements wouldn't be limited to drug development. Quantum computers could also be used to design new materials with specific properties, leading to advancements in a variety of fields.
That's right. Imagine being able to design materials that are stronger, lighter, more durable, or have unique electrical or magnetic properties. This could revolutionize everything from construction to electronics to energy production.
The document estimates that we could see practical applications in drug discovery and material science within the next 10 to 20 years. This timeline highlights the complexities involved in applying quantum computing to these fields.
It's important to note that these are just estimates, but they provide a sense of the time frame for when we can expect to see tangible benefits from quantum computing in these areas. Beyond those applications, the document also highlights the potential of quantum computing in addressing global challenges like climate modeling.
Climate change is an incredibly complex issue, requiring sophisticated models to understand and predict future scenarios. How could quantum computing advance our current climate modeling efforts?
Classical computers have made significant progress in climate modeling, but they're limited in their ability to handle the vast amounts of data and the intricate interactions involved in climate systems. Quantum computers, with their enhanced processing power, could take climate modeling to a whole new level.
So we could create models that account for more variables and interactions, leading to more accurate and detailed predictions of future climate scenarios.
Precisely. They could allow scientists to create more accurate and detailed models that take into account factors that are currently too complex to model, such as cloud formation or ocean currents. This could lead to better predictions of future climate scenarios and more effective strategies for mitigation and adaptation.
The document estimates that we could see the impact of quantum computing on climate modeling within the next 10 to 20 years, similar to the timeline for drug discovery and materials science.
This time frame reflects the need to develop specific quantum algorithms and models tailored to the complexities of climate systems. However, the potential benefits for understanding and addressing climate change are substantial.
Finally, the document touches upon perhaps the most intriguing and speculative application of quantum computing: artificial intelligence. But it suggests a much longer timeline for this, 15 years or more.
AI, particularly machine learning, relies heavily on algorithms that are optimized for classical computers. Adapting these algorithms to take advantage of the unique capabilities of quantum computers is a complex task, requiring new approaches to algorithm design and implementation.
So it's not simply a matter of running existing AI programs on a quantum computer and expecting a significant improvement. We need to develop new algorithms specifically designed for quantum computing.
Exactly. It requires developing new algorithms and approaches that are specifically designed to leverage the strengths of quantum computers for AI applications.
But if we can overcome these challenges, what kind of advancements in AI could we potentially see?
The possibilities are vast. Quantum computers could significantly speed up the training of machine learning models, allowing them to learn from much larger data sets and solve more complex problems. This could lead to breakthroughs in areas like natural language processing, image recognition, and even the development of truly intelligent systems.
So while the timeline is further out, the potential for quantum computing to accelerate advancements in AI is immense. However, it's important to acknowledge that these are all potential applications, and quantum computing, while promising, is still a relatively young field.
That's right. It's important to manage expectations and acknowledge the challenges and limitations that still need to be addressed.
What are some of the key challenges highlighted in the document that researchers are still working to overcome? The document acknowledges that quantum computing is still in its early stages of development, and there are significant challenges to overcome before it can reach its full potential.
One of the most fundamental challenges is decoherence. It's the tendency of quantum states to lose their coherence due to interactions with the environment.
Could you explain why decoherence is such a significant hurdle for quantum computing?
Quantum computations rely on the precise manipulation and preservation of delicate quantum states. Decoherence disrupts these states, introducing errors into the calculations. It's like trying to build a house of cards in a windstorm. The slightest disturbance can cause the entire structure to collapse.
So, maintaining the coherence of qubits long enough to perform meaningful computations is a major engineering challenge.
Precisely. It requires incredibly precise control over the environment and sophisticated error correction techniques to counteract the effects of decoherence. Another significant challenge is the lack of a universal quantum computer architecture.
What do you mean by universal architecture?
Currently, there isn't a single design for building quantum computers that is clearly superior to all others. There are various approaches, each with its own strengths and weaknesses. For example, superconducting qubits, like those used in Willow, require extremely low temperatures to operate, which adds complexity and cost.
So there's still a lot of research and development needed to determine the most effective and scalable architecture for building practical quantum computers.
That's a fair assessment. The development of Willow is a significant step forward in terms of scalability and error correction, but it's just one approach among many. It's likely to inspire further innovation, leading to the development of even more sophisticated architectures in the future.
Beyond the hardware challenges, the document also mentions the need for more robust quantum software and a larger pool of skilled quantum programmers.
That's another crucial aspect. Building a powerful quantum computer is only part of the equation. We need to develop the software tools and algorithms that allow us to effectively harness that power to solve real-world problems.
So it's not just about the hardware. It's also about having the right tools and expertise to make quantum computing accessible and applicable to a wider range of problems.
Absolutely. We need to create user-friendly programming interfaces and develop quantum algorithms that are optimized for specific tasks. And just as importantly, we need to train a new generation of quantum programmers who can bridge the gap between theoretical quantum physics and practical applications.
It seems like there's a need for a multidisciplinary approach, bringing together physicists, computer scientists, engineers, and even experts from other fields to fully realize the potential of quantum computing.
I completely agree. Quantum computing is a field that thrives on collaboration and cross-disciplinary expertise. It's through these collaborations that we can address the challenges and unlock the full potential of this transformative technology.
The document also cautions against hype and emphasizes the need for realistic timelines when discussing the potential applications of quantum computing. Why is this important?
Quantum computing is a powerful tool, but it's not a magical solution that will instantly solve all of our problems. It's important to manage expectations and understand that it will take time for quantum computing to mature and reach its full potential. Some applications, like optimization problems, might be realized sooner, while others, like complex drug discovery or advanced AI, will likely take much longer.
So it's about finding the right problems for quantum computing to solve and focusing on developing practical solutions that address real-world needs rather than trying to apply it to every problem indiscriminately.
Exactly. We need to be strategic and selective in our approach, and we need to continue to invest in research and development to overcome the challenges that remain. Despite the challenges, the progress being made in quantum computing is truly exciting. It's a field with immense potential, and it's a journey worth following.
Thank you for this insightful discussion. It's clear that quantum computing, while still in its early stages, is a field with profound implications for the future. It's a field that sparks both curiosity and a sense of wonder. Who knows what amazing discoveries and innovations await us in this uncharted territory?
Indeed. The possibilities are vast, and the future of quantum computing holds immense promise for transforming our world in ways we can only begin to imagine.
And on that note, we'll wrap up this deep dive into the world of quantum computing. Until next time, keep exploring, keep learning, and keep diving deep.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.